After autoregressive model, we have a more advanced variant of the regressive model, which are called neural autoregressive. So anything that has to be advanced has neural these days. So distribution estimation. Okay. So previously, what we have seen is that so our goal to start with is to estimate this, having seen up to t, before t, how to learn the probability density to predict the tth word in a sequence. Okay, so this kind of problem could be like I am going to, and then predict the next. Okay, so this is the prediction problem where x1 is this, x2 is this, x3 is this, x4 is this, and then you are asking x5 is what. Okay, so these are the problems we are looking at. Compared to what we have done previously for image generation, these are different type of problem. These are sequence problems. Having seen some words, can you predict something? Okay, so this could be modeled as a conditional probability. Okay, so given this, what are the predictions you can do? Obviously, there could be many options here, but it also depends on what I have seen. Okay, so in this case, it may say many things. I'm going to school, I'm going to market, so many things can be, but then if you have more and more specific conditions, then it will try to learn more specific word to predict. And in fact, the whole idea of the ChatGPT is just this. Okay, and the philosophy behind ChatGPT creators is that if I have a model that learns how to predict the next word, that itself is a big deal, because it's a big deal because knowing how to predict the next word also essentially means that the model has learned certain understanding of the world. Basically, it knows, it has somehow encoded a good representation of the world with the text that it has seen, and it knows exactly or kind of like in a very high probability what could be the next. So just saying that what is the big deal in predicting the next word, there is a big deal because predicting something given what you have seen means that you know a lot about the world. Okay, hence you know what to predict next. Okay, so hence we are looking into this type of models, which are these sequence models, and the whole idea behind these today's and then the 2-3 classes is just to understand this type of problems. And we started with a linear regressive model where we are saying that xt is related in a linear way to t minus 1, and then with that I am saying what is the probability distributions when I see next xt coming from some linear scaling and translation of the previous xt, then how will my distribution evolve if I change my my random variables linear way. So there are many ways to change random variable. I change x t to xt squared to sin xt, or the linear is like xt plus c. So these are the things we have seen. So linear we have seen. So when I change random variables like that, my distribution changes obviously. So you get in exam questions like this follows some let us say some distribution uniform something, find the distribution for this. Okay, so you do some change of variables sometimes and so on, right? Formula transformation formulas and so on. So here so we started with the basic one. We do linear transformations of the random variable, and then we want to see how the distribution evolves. So if I have a template distribution normal, then I'm saying does it evolve with a normal distribution with some different mean and variance? That's what we expect. Okay, so these are the ideas we are working with. And so linear was a very simple one. Okay, so just dependence on the previous xt, and then the idea is to generalize this to some nonlinear transform. So I have shown you like this could be some nonlinear transforms, but then we want to do it in a way that it helps in solving problems like this. Okay, so this is the problem we are solving, and we will basically generalize the linear transform. In fact, we will put a neural network. That's the idea. Okay, so we'll put a neural network with a parameter, and in the linear regression model, you had this row, and this row is the regression parameter basically. Okay, so that's, you can think of this as a parameter of your network. Okay, so given the data you have, how parameters I am going to change, even if it's linearly, how I'm going to change the parameter. Okay, then I'm going to kind of, so I will learn these parameters via this these labeled data. Okay, now maybe it's a good idea also to tell about this. So if I have to build a basic machine learning model to predict this, what I can do is that I can look up a lot of sentences, and then what could be the possible next word. So you pick some textbook, and then you create a label data like this, X, and the label is Y. Okay, so you can have many sentences, and then you note down what is the next word in the sentence. Okay, so let us say it I am learning, and then let us say machine learning. Okay, so I am happy, the cat is dancing. So you see, you pick up any book and you create data like this, and it may not be only the last word in the sentence. It could be also some 3 words and then the next word. Okay, so it has been raining. Okay, let us say I remove this one. Okay, it has, okay, let us say been, and then raining, and then there was few more things since yesterday or something like that, but then I just want to predict raining, let us say. Anything. Okay, the point here is that anything that makes sense. It has been raining, it has been something else also. Okay, so it doesn't matter. The point here is that you create a label data that that has this features and then the labels. It's like the, what is the next word is your label. Okay, so this is a supervised machine learning problem, but the only difference is that this is a sequence, because the features here have some ordering. If you change this in other way, am I learning, then it's not the same sentence. So the ordering matters. So first is this one, second is this one, third is this one, and then you predict this. So this is a machine learning problem, but then the ordering of the input is important. That's why we give a ordering x1, x2, x3. So as such, you can see it's kind of a simple model in itself, where I generate a lot of label data like this, and I let the model predict what could be the next. So this prediction that we do, right? So this x1, x2, x3, these are the features, and then we are trying to learn a function, let us say some neural network function with the parameter theta, and it will give me the next word prediction, let us say x10. Okay, so this is what we are trying to do. I just write this in a probability notation that having seen up to t, okay, let us say t minus 1, what is the prediction for t? So that's, so earlier models used linear. I mean linear in the sense like they see that the next t is linearly dependent on the previous t, but then the recent models use neural networks basically. Neural networks are the most powerful prediction functions you can think of. So whenever you want to have predictions, very likely you would like to complicated predictions, then very likely you insert neural networks. And this is what these autoregressive models were very old, but then since neural network came, then people thought, okay, since they are very powerful in predicting, understanding relationship between data and predicting something useful from there, so then they use now neural network. The only thing is that all this has to be all this we have to fit in the sequence modeling framework, and this is what we are trying to do. So some of these models now, basically the neural models are now used in some latest to put it in the context. So what we had previously is that we had the linear regressive model, so which is xt minus 1 minus mu plus, okay, basically this type of linear relationship we had, and we also added the epsilon t, let's say, for randomness, but this is the linear relationship we had in the autoregressive order 1, and what we want to say is that we replace this linear by a function by some nonlinear neural network. Okay, so the next step is we replace linear function with more expressive nonlinear functions. And these are parameterized by neural networks. Okay, so we look into this nonlinear functions which are neural networks and parameterized by the neural network parameters. This is the extension we are going to do, and this kind of idea is now more or less used by ChatGPT also. But we will see that everything now boils down to choice of f. And what is also interesting is that there is hardly much maths here, because it's a lot of kind of engineering, like what kind of f we will choose. Not much proof is there. So basically f is neural network, so and there is many possibility to choose variants of neural network. It could be CNN, it could be RNN, it could be LSTM, transformer. So whole discussion will go into neural network now. So with this kind of model, now you have some, with this, we have some recent generative modeling results. In NLP, so NLP is like natural language processing, natural language processing. So if we look into some of the references, so one of the reference is language models are unsupervised multitask learners. So this is by Radford et al. And the title is language models are unsupervised multitask learners. And this was in 2019. Okay, these are all kind of ingredients, similar ingredients goes into like ChatGPT stuff, and Radford, and then there is Brown 2020. So it's good to note it here. What is this reference? Yeah, language models are few sort learners. Brown, and then language models are few sort learners, and this was 2020. So the idea here is that these autoregressive models, which started with some linear modeling, then extended to neural networks, and now these are the main ingredients behind this recent success of these generative models. In fact, ChatGPT is exactly this paper. Okay, so we will see now how exactly this f will change. Okay, and there will be like computational issues, right? One of the computational issue you see is, do I need to look into all the previous ones, right? Because sometimes the sequence can be very big. So depending on sequence length, if you keep track of all previous t, then the computation will be very heavy. So should you assume some Markov assumptions, you depend only on previous t. So these are the computational issues. Okay, and we will see some tricks used with the help of neural networks. So let us build on this idea how we can have more expressive neural networks which can capture these previous dependencies. And so we start with something called fully visible Sigmoid belief network. So this is by the first proposed by Neil. So I'm going to kind of just note it down here. So this network is proposed by Neil, and this is called connectionist learning of belief networks, and this was 1992. So this as such was old idea. So without going into too much of this, let us define these sigmoid belief networks. So I define this using definition. So let P be RT and define Ft that goes from RT minus 1 to R by Ft of x less than t, inner product of P less than t, x less than t, then the fully visible sigmoid belief network is given by xt follows Bernoulli sigmoid of Ft x less than t and x1 Bernoulli of T0. Okay, so this is the definition of sigmoid belief network, fully visible sigmoid belief network. And sigmoid is a function, sigmoid of I can define it separately. Bernoulli is the distribution here. So sigmoid is a function which is given by 1 by 1 minus e to the minus u. The sequences, it's good to note that these sequences in this network are taken to be binary sequences. So meaning that they come from basically the goal is to predict xt in 0 1 using a log linear combination of x less than t. So this is a sigmoid belief network, and you can see this is an extension of the linear where now xt now depends on x less than t, all the previous ones, and then it is applied by some ft, okay, some function, and top of that you apply sigmoid, and this is the parameter for the Bernoulli. Okay, the Bernoulli distribution has parameter p, right? The Bernoulli has a parameter p, it's like head or tail, right? So basically we in our model we are modeling these sequences as a sequence which is being predicted as heads or tail basically. Okay, so given a sequence of 0 1 0 1 0 1 something like that, what do you predict, 0 or 1? Okay, so overall all this means like that, because these x are sequences 0 1. Okay, so this is a very simple model. Let us say 0 0 1 0 0 0 1 1 0 0, and then this is, let us say, less than t, and these are your x less than t. So this is my x less than t, and on top of this I applied ft, okay, and this on top of this I applied sigmoid, and sigmoid, as you know, is a value between 0 and 1. Okay, so sigmoid lies between 0 and 1. So this will act like a probability p that lies between 0 and 1, and which is what the probability values in this case are supposed to be. The probability values lie between 0 and 1, and those are parameters for the Bernoulli. Then the prediction will happen with that probability. Basically, you learn the Bernoulli, and then you will sample the t from the distribution whose p, the probability of having a head, let us say 1 is the head. The probability of having head is, let us say, 90%. Then it's very likely that your xt that you will sample at the th time step will be 90, right? So, but then to understand this complicated relationship of the sequence that I have and what is the probability that it gets generated, which number gets generated in the next in the sequence, is a complicated relationship which I may not be able to understand from the data. So I let it kind of learn on its own, and I let it learn on its own because I know that I have many label data with these kind of sequences. So let us say 0 0 1 0 0, and let us say the sequence length is 5, and then from the data I'm just looking at the data, I thought this was 1, and then 1 0 0, this was 1 0 0 1, this was 0, like this. Okay, so this is my data. So the function f, which is my neural network, it will tune its parameters. If the error is high in predicting the next xt, then it will do a gradient descent. It will update its parameter, and next time it will try to improve on these predictions. Okay, so this, you can think of this as a very a simpler case where your xt's are just binary numbers 0 or 1. Okay, and these complicated relationship is understood from the data by tuning the parameters of the neural network each time we will see. And if the p that you learn, the sample that you got, so let us say you did the first step, you did the training on, let us say, 3 or 4 samples. Okay, and initially your weights were some random, you updated using gradient descent. I mean, okay, let us not go there right now. So let us say first data came. So let us say the first data is 0 0 1 0 0. It went there. The weights of the model are not known to me initially, so I put a random. So, and then this will give me a probability p, and since my initial weight of the model is random, so maybe I don't have any understanding basically, so it will give me a p which may be very bad. From there I sample, and let us say I sample which is 0, which is very likely. Okay, so I sample is 0, but I know that it was supposed to be 1, so hence I will go there and change the weights of the network with a suitable like loss function we will define. Okay, so we will come to that in detail. So we will say, okay, you did bad, update your weights via gradient descent or ascent depending on which type of loss I build, and then next time the next sample will go 1 0 0 1 1. So now the weights are a little bit updated, learning from the first example, and if it does again bad, it has given me a parameter p for the Bernoulli, which is again giving me, let us say, for the second sample 0, but I was supposed to get 1. So again it will update the weights of the network. So it will keep doing this training. Okay, and until it will learn a true distribution, because Bernoulli is determined completely by the p. Okay, so basically you can think of this as coin, but this coin has bias, so there may be more head than tail and things like that. So this is what we are trying to understand, right? So once we have learned this p correctly, then you know that, okay, I have learned it, and now I can, having seen data point up to certain amount, I know how to predict the next word in a sequence. Okay, so this is a very simple case. This is what we will generalize to words. Now you can extend the same idea to words in a sentence. It is binary, but then in words it will no longer be binary. It will be multiple values here. In this case, you have only 2 classes to predict, so you can get away with the binary classification. But then there we have multiple classes, because the next word in the sequence could be any word in the dictionary. Okay, I mean technically any word in the dictionary, but it will have limitations because only valid words, only a very restricted amount of words follow after certain words, given set of words. So this is the idea behind these Sigmoid belief network. So as I said, everything now goes into modeling. Okay, given a set of sequence, which function you are applying, okay, and which distribution you are approximating. So all what we will do in the remaining classes will just look into these. Okay, so if it is a discrete problem like this, then you follow this. If it's a continuous, then you use some continuous distributions. In this case, Bernoulli is a discrete probability distribution because the model is like this. But if you prefer continuous, then you may go for the continuous model. Okay, so these are the things we have. So with our notation in the Sigmoid belief network, they choose f to be like this. which is nothing but the inner product of x with p, and p is a vector basically, okay, of length t, let's say, and or when I do inner product, whatever the length of x less than t is, it will be of the same length. Okay, so it is not linear. You can say that this is weight times x and it is looking like a linear, but it's not linear because of this, because you are applying some non-linearity, which is sigmoid, which is 1 by 1 minus e to the minus mu minus u, right? So this overall, if you leave it until here, then it was linear, I agree, but then because of this, it's a non-linear model now, so it's an extension of the linear model. And it was as usual, in the autoregressive we were taking a normal, but here we are taking Bernoulli. Okay, so weights of our network is p here. Okay, this is the p that we will try to learn from the data we have. Each time it does badly, we will update using gradient descent and update the p matrix each time. Okay, so this is what we know about this very old paper 1992, the sigmoid belief network. It was applied on some these binary problems basically. So some of the remarks that we see from here is that the weights kind of are shared. These weights, if you see, are being shared as we go ahead and build conditional probabilities for xt, t plus 1, and so on. So to explain this, so what we are looking for in general in this generative modeling in the sequence models is like this. Okay, so we are saying is that show me the probability distribution of xt given that you have seen up to t minus 1, and for each different values of t, I may have a probability distribution which have its own parameter. So by this I mean that let us say some distribution, right? So with, let us say, normal with mean and variance, and then I may have let us say so what might happen is that for each t, I may learn a separate probability distribution with separate means. Okay, so in this case, as you can see here, so if I draw it as a graph as x1, x2, x3, x4, x5, x6, and if I see x1, x2, x3, let us say, then I predict, let us say hat is my prediction, okay, x4. So the weights of this that I used in this case, let us say we go by these weights, right? Or I use some generic weights, let us say w1, w2, w3. Then these are this is my prediction. And then if I have to predict the other ones, let us say x2, x3, x4, then x5 hat. Okay, then the weights that now go from x2 are different. Okay, so this is now so let us say w14, w24, w34, this is w51, w52, w53. So the edges that come from x2, x3 earlier where the weights were w42, w43, but now the weights are w51, w52. So this is a different network with its own weight predicting x hat 5. This is a different network with its own weight predicting x4. Okay, so your model complexity will be very high if you go like this. So so that's one way. But if I look into this, okay, then what is happening here is that the parameters are being shared here. So if I change to this p are the weights are the same. If I am changing to different variants of t, obviously if my t changes, then if it increases, then p the dimension of p also increases, but then they are they are shared. Okay, so this is the same weight. So basically this is that this W24 and this W25 are the same. I mean they are the same weights. Okay, and then W43, W45, they are the same weights. This is called weight sharing. Okay, so this is called shared parameter network. So depending on the next words in the sequence, you update the weights that you had already. You don't create new weights. Okay, so that I mean this is what is happening here as well. If I change the t, then the previous piece don't change. Okay, so let us see this example first. So let us say this is my f3, so x less than 3. So this is p1, p2. So this is p3, p2. Okay, less than 3. P1, P2 inner product, and then this is x1, x2. Okay, so this is P1, x1 plus P2, x2, and if I look into P4, x less than 5, then this is P1, P2, P3, P4, and x1, x2, x3, x4, and this is P1, x1 plus P2, x2 plus P3, x3 plus P4, x4. So what we see from here is that the weights that go with x1, x2 and x3 are the, I mean x2 up to x2, let's say, and the weights P1 and P2 are the same weights. I'm not changing the weights completely when I'm seeing up to 5. I'm using the same weights, and then next time I will say same weight that I have seen data up to x2, and now that I have seen data up to x4, if there is a change needed in the weight P1 and P2, then go and do it. Overwrite the weights that you have learned when you seen up to x2. So this is called parameter sharing network. Okay, so as I explained here, now if I was up to 5, I could have taken this to be different P1 and P2, but we won't do that. Okay, we will keep the same P1, P2. Okay, so these are the concepts people use in things like RNN and something. We will come to that in more detail, but this is called parameter sharing. Parameter sharing in a network. Okay, so we will see a little bit more of this later on, but for the moment I believe you understand what I mean. Okay, is also evident from here. So this is one thing, is that we share the weights at each location in the history. We are sharing the weights at each location in the history. We didn't change the weights in the history if I had more words in the sequence later on. So that's an important point. In fact, this is the principle behind other models that we will study, like RNN, LSTM, transformers. Okay, so we can write this in a more compact form, in the sense that, let us say the maximum sequence length I have in the data is, let us say, given by T, capital T. Then we can kind of write this in a way that it's defined for T, but then we only use up to small t. So using something called mask. So this is just a kind of a notation change. So the idea here is that if my sequence lengths are t, so let us say x1, x2, x3, xt, this is my first sample. Okay, and then I do predictions, and then let us say this is my second sample. So this is, let us say, first sample, this is second sample, and so on. So this sample length t are there, but then like I see so these are like the maximum sample lengths I have, but then when I'm learning, I'm seeing up to 3, up to 4, things like that. So we can make a notation in a way that it's compactly written using some marks. So let us say I see only up to 3, so I can create a vector that only looks into the 3 and makes other 0. Okay, so we can define a mask like this. Okay, so we have created a mask MT, and this MT is defined as MT, and the S component of this MT vector is 1 whenever S is less than T, and it's 0 otherwise. Okay, so this means that this is 1 if S less than T and it's 0 otherwise. Okay, so as you can see, I have created a mask. So if I am at a T, then only up to T M has 1. So basically it will only fetch T entries of X and make other 0. So that will not have any effect on the inner product basically. So that's a different way to write the same term. Rather than writing less than T, we just write this, and this less than effect is created by MT by taking only putting 1 on those first less than T values of X and making other 0. So this is called masking, and this allows us to write this compactly. Yeah, I will extend this to categorical. So in this case, it's basically we can extend this to multiple classes. So now in this case, we are dealing with the output is like Bernoulli. So Bernoulli output is like heads or tails, 0 or 1. So then the question is like, can you extend this to k classes, let's say, okay, or number of words in the dictionary, let's say, which could be the possible predictions as the next step. So I want to kind of extend this to this. So for discrete time series, W that comes from the vocabulary, let's say T, the number of words that you have, let's say, of length T, then we can replace Bernoulli with a categorical distribution and parameterize the modulus softmax. So basically we use softmax. This is another function which is used to extend the sigmoid basically, because sigmoid keeps between 0 and 1, right? So here we have this softmax of U is EU divided by sum of UK, k equals 1 to D. So softmax applies on a vector. Okay, so U is a vector, and basically it gives you the probability values, but now now it gives you a vector. So in this case, in the earlier case, we were looking into 0 or 1, probability for 0 or 1, but now it will give you probability values for multiple classes. So let us say cat, horse, dog, and so on. So it will tell you here, okay, the percentage of this is, let us say 0.9, 0.01, 0.1, okay, not 1, okay, 0. Let us say this is 7, this is 1, and so on. Okay, so softmax, what it does is that it gives you these probability values for multiple classes, not just 2. Okay, so then from there you can say, okay, so how I mean, looking at these probability values, you can say that, okay, most likely it's a cat. Okay, so this generalizes to the multiple classes that we have. Okay, so we can extend this Bernoulli, and we change Bernoulli to categorical, and inside we have softmax. So looking at this, then we will decide which class it belongs to. So, and another thing we need is that we also need to encode the history W less than T by embedding it in Euclidean space. So basically it means that we will give some representation for these words. So let us say earlier we were using X, but we are using W. These are, let's say W stands for the words. So when we see these words, we want to give them some vector notation so that they are distinct. So one possibility is that we do one hot encoding basically. So let us say there are so if you have a dictionary with let us say 100 words are there, so which vector representations I give to the words so that they are unique, right? So one possibility is called one-hot encoding. So one-hot encoding means that the word I is given the representation EI, where EI is the ith column of the 100 by 100 identity matrix. So this is like the ith column of 100 times 100 identity matrix, right? So this is one way we can represent each word so that they remain unique. They have unique representations. So when we have words, binary case it was 0 or 1, but here now we are thinking of words that could be, there could be many words, and each words need to have vector representation, and that's what we were going to, that's what we need, we mean by saying embedding in a Euclidean space. So in that case we can, so one-hot encoding is used. Let us say like this. So one-hot encoding is each word, so each word, let us say Wi, is encoded as EI, okay, where EI is defined there. So with this we can now define the fully visible sigmoid network to multi-class case, okay. So that's what we will do. So this is definition 2, and this is let P be in R T by D by D, and define Ft from R T minus 1 D to Rd by Ft less than T P S XS S less than T. So we will define this Ft as a linear combination basically. So PS are our weights. So we apply the weights for each of these sequence XS, and then with this we define the fully visible softmax belief network is given by Wt, which is now some categorical distribution, and softmax of f of t x less than t, and then W1 categorical P00. All right, so this is our extension of a binary case to the multi-class case, and we change the sigmoid to softmax. So softmax works on a vector, okay. So and it produces a vector also, and then we have some categorical distributions, okay, depending on the problem at hand. So this is the model we have, and inside this Ft we have these are the weights of our network, and these XS are actually the WS W itself, okay. So here I can write this as here, okay, just for we are going back to our original notation. So here the XS is WS, okay, the sth word in a sequence, and these words are encoded as a vector, okay. And so these are like ith column of the identity matrix, and then we have these weight matrices P multiplying on these vectors. So this is D by D multiplying to D vector, okay. X S is like D, it takes the X, okay, but here for a fixed S it's D by D length vector, and it gets multiplied by the D by D matrix. I'm trying to explain additionally, everything is fine, but I'm just trying to see if there are other ways also I can explain. So the way it is happening is we have these X vectors which are the words in the sequence. So the way this is now is, let us say we have X1, okay, then we have X2, and then we have, let us say, xt. Then these words have encoding in the form of the E metric, E vectors. This E1, E2, E T. Okay, so and each of these E are d-dimensional. Okay, so these EI are d-dimensional. Okay, and these D is also the number of classes we have, because the places where I put the 1, that represents certain word. Okay, and if I put here, then it represents certain word. Okay, and I will see some sequence of these, right? So within this up to T, I will see some sequence. Let us say I will see like this, and then the second one I will see will be like this. The third one I will see will be like this. And what I may have to predict is maybe like this. Okay, so these are our x1 in the sum, x2, x3. Okay, and what we are supposed to predict, let's say, is this. It's not a coincidence that it is there, it could be anywhere, but let's say this is the word that we are supposed to predict. Okay, so then these P are the weight matrices. Okay, and these weight matrices are kind of like it multiplies on each of these basically. Okay, so the weight matrices I can define is P11, P12, P1. Apply the masking. No, there is no masking. It just applies on S. Okay, let us do that. PS P is d by PS is d by d. P as a whole is a tensor with all the time up to T. What I'm wondering is, this was also supposed to be a shared parameter network. So why should I keep a T copy of capital T copy of P? This is my confusion right now. Maybe there is something I'm missing, but this is P1D and this is PD1, PD2, PDD, and I believe the way it is like this, and this multiplies to these vectors basically. Okay, so for P1 will be multiplying with this, P2 will be multiplying with this. Okay, that makes sense, right? Okay, so if we now write down this ft x less than t, so if this is the sum, right? So let us say we have P1, so P1 will be P111, P121, P1D1, P211, P221, P2D1, PD11, PD21, PDD1, and this gets multiplied with the first one, which is x1, which is E1. I mean, we are writing x1 is E1, but it could have been anything, E1 or E10 or whatever, depending on initially what encoding we get for the word. But it's not necessary that those each sentence starts with x1. It's not necessary, obviously. So it could be something, right? EI1, let us say, plus, and then we have P112, P123, P1D2, and then this is 2, then there's PD12, PDD2, and this multiplies with EI2. So this is our F calculation going on here, and this will go until T. Interesting thing to note here is that this is still a parameter sharing network, because for a given sequence E1 it remains the same. Okay, so if I increase the sequence to K, these P's didn't change, they remain the same. It will get updated basically. So now if we look here, so for x1 x2, to compute x1 x2, I needed this P1 matrix and P2 matrix. Now if I have to compute X3, then I keep this P1, P2 and P3. So it is still a parameter sharing network because I did not change P1 and P2. I did not completely change P1 and P2. I updated. I will update, but I will update the same weights. I will not make a different model next time. If I have to compute for P1, P2, P3, I will not make different model separately. It's just that now these are now matrices, and yeah, so each of these P are matrices, and then a collection of these, if I go up to sequence capital T, then indeed I am with this will be a tensor, D by D matrix, D by D matrix, D by D matrix, and then if I take them as a collection P, which is a stacking of these tensors. So this way we have P1, P2, so together it will be a tensor. This dimension is T and this is D by D. Okay? So this is how we see this when we generalize to multiple classes. Okay, so I think we can stop for today. We will continue with this in the next class. Okay.